In the name of God, the compassionate, the merciful, engineering plasticity, Chapter 5, Elastic Plastic Analysis of Bending, Part 8. Continuing from the last two previous parts, we are going to solve some examples using the collapse load. Now, in here, I have illustrated a link, an oval link, as you can see, like that. There is a force P applied here and applied there. This could be a member of a chain, okay, a chain member. So we want to know how much load we can apply here, maximum load that is possible to apply here. Okay, so we are going to use the collapse load technique. Now, how do we do that? First of all, we must consider this as a mechanism. Okay, if we want to consider this as a mechanism, these blue lines that I have drawn are not part of the link, but just drawn to show the geometry. Now, that's C1b and C1a. If I continue this over here, I find point I, which is the instantaneous center of these points. What is this instantaneous center? If we consider this C1b, this arc here, as one member and C1a as another member, then pulling these 2 points apart, it means that B and A move apart from each other and C1 moves that way. So we consider the velocity here omega, small omega and big omega in here. Okay, so that's the instantaneous center. Now let's have a look at which points could be the plastic hinges. Plastic hinges are A, C1 and B. Okay, this is relatively logical. You can take, for instance, these points as plastic hinges as well. But first of all, we are going to take the easy one, which is this one. And this link is symmetrical about the vertical and horizontal lines. About BA and C1, C2, the link is symmetrical. Okay, so I'm just going to consider half of the link. Now IB, I is the instantaneous center. IB times omega is equal to 1 meter per second, because I'm considering point B to be moving 1 meter per second. If I consider point B to be moving with a velocity of 1 meter per second, then that is correct, okay, because that's the instantaneous center, that's the angular velocity. So the angular velocity is 1 meter per second divided by IB. Similarly, for this link, this line, and that line, I can write IC1, sorry, for this link, IC1, I can write for IC1 times omega, because IC1b moves with angular velocity omega. So I can write IC1 omega equal to AC1. Okay, this one is moving with this big omega, capital omega. So AC1 omega. So the big omega or capital omega is equal to IC1, where AC1 times small omega. And since I'm considering half the link like that, then this P is divided by 2. And you can compare this with the previous examples that we solved, like the built-in beam and that frame. It's almost similar to them. So if we write P over 2, P over 2 is equal to 2, of course, p over 2 times 1 meter per second, because it's moving 1 meter per second. So p over 2 times 1 meter per second is equal to, now we got 1 m here, mp, another mp in here, another mp in here. Now mp in here is times omega, mp in here is times big omega. Now I would have, so that is 2m, that's m times small omega times big omega. I have also another mp in here, but I have 2 mp in here, you see, because it's moving, one is m small omega and one is m big omega. Previously, because these two velocities were the same, I would have written this 2m times the velocity. But here I have 1m times small omega, another m times small omega. So I get all together 2m times omega plus omega, because I have 3 points. Now, one point is this m times this omega, another one is m times this omega, and this one has 2 m times this omega and m times this. So I get all together p over 2 equal to 2m times small omega times big omega. Right, then I substitute here. So if I take this 2m, bring it into the denominator, I get p over 4m, and substitute for omega, which is 1 over ib, and substitute for big omega, which is IC1 over AC1 times small omega is 1 over IB. So if I substitute all of these in here, I get IC1 plus AC1 over AC1 divided by IB. Now this is equal to 1 over C1n, because I have these similar triangles. The big triangle is AIB, and the small triangle is AC1n. So C1n divided by IB is equal to AC1 divided by AI, and that's what I have here. So 1 over C1n is equal to this, and therefore P over 4m is 1 over C1n. So if I clearly, if I have this link, I have this distance, and I have, depending on the material used for this link, we could have the maximum plastic bending moment, and so that maximum plastic bending moment times that divided by that is equal to P, which is the maximum load. Now let's consider another example. Now in this example, I have an stud link. That is a stud link. So I have this oval link, and then another link inside it. That is a solid link. I have put inside this oval link so that to reinforce it. I have reinforced the previous link with one more link, which is called a stud link. Now in here, I have considered these plastic hinges, 8 together, okay, 8 plastic hinges instead of 4 plastic hinges, so, or 3 plastic hinges. So if I consider a quarter of the ellipse, it's like that, a quarter of ellipse, because there is symmetry, and that is that line, black line is the ellipse. Now I have taken a point C somewhere along this curve and connected B to C, and also this vertical line, I get this I, which is the instantaneous center for this case. Now here again, because I'm pulling this apart, so it moves the member, the black member there, moves with the velocity of small omega, and the black member here also moves with the velocity of big omega. Okay, so this is how this link moves. If that is the plastic hinge, that is the plastic hinge, and that's the plastic hinge. These three plastic hinges. Now, where is C? We want to find out where C is. Okay. So I connect A to B as well. This I is the instantaneous center. So this P over 2 is moving with velocity of V of VA. Okay, we call it VA. It's velocity VA, and find out where this plastic hinges. Okay, and then we could find out how much P is. Now we could guess where this C is. You see, I think this point C, this distance Y, QC. In fact, QC or Y at its biggest value, when QC is the biggest value, that point C is determined because for the collapse to occur, this must be maximum. Okay, so I will explain why CQ must be a maximum later on. I have written this again. It's just like before. For this link, here we have P over 2. We have one plastic hinge, two plastic hinges, and three plastic hinges, just like before. So the velocity is VA. P over 2 is moving VA with the velocity of VA, and 2m times omega plus omega, just like the previous example. Okay, so I can write P equal to 4m over VA omega plus omega. So I have to find out how much the values for small omega and big omega, and then I can find P. Now the big omega, that we say is VA divided by IA. Since IA is the distance from the instantaneous center to A, so this link moves with the angular velocity of VA over IA. And similarly, I can write this big omega times IC, and the small omega times BC. Okay, BC times omega, IC times omega. And so I can get this small omega in terms of big omega, or vice versa. Big omega in terms of small omega. So here I have omega times BC over IC. Okay, that is the big omega, small omega times BC divided by C. IC is the big omega. So this big omega times IA gives me VA. Okay, that's the angular velocity, that's the linear velocity. So if I substitute all of these in here, I get P equal to 4m VA. I have obtained it from here, so I put it here. Also, I have this small omega, and I substitute for the big omega. Big omega is equal to omega times BC over IC. Okay, so everything here in terms of the geometry and small omega. And let's see what we have here. So if I simplify this, because these omegas cancel out, so I've got only these lines, the geometry, and m, so I can get P. So I just have to get these values. Okay, now I simplify it further. So 4m times IC divided by BC plus multiplied by IA is equal to BC plus IC divided by IC. And so P over 4m BC plus IC here divided by IC. This IC with this IC is cancels out. Denominator is BC times IC, and that is IB, because IB is BC plus IC. Okay, so that's what we get. Simplifies to that. Now, in here, in these triangles, this big triangle, the small triangle, I can get CQ divided by IA is equal to BC divided by BI. So I've got IB or BI here, and I got BC here, and I got IA here. So I could substitute for these from here equal to CQ. So that's 1 over CQ P. Instead of this, I put 1 over CQ. And CQ is equal to Y in here. So, as I said before, as C moves on this link, we reach some point that CQ is maximum. Okay, that is where the hinge is. We can see here that if Y is maximum, that P over 4M becomes minimum, and that's what we want for the collapse load. So if Y becomes maximum, we get our answer P over 4M. Okay, so we are going to obtain Y at the maximum position. We are going to point to find out point C, the position of point C, such that Y is maximum, so that it gives us the minimum for P over 4M. So, in order to find out how much Y is, or CQ is, I use the equation of ellipse. Okay, for this curve is part of the ellipse, so equation of ellipse is that, and OA is equal to A, OB is equal to B, and minor and major values for the ellipse. So line AB, also line AB, is mx plus c. That's the equation of line AB. That's the equation of line for the ellipse, the curve for the ellipse. And here I can write down y equal to b over ax plus c, because that's where y is 0 and y is 0, x is equal to this distance OA, which is A, and x is 0, this line is equal to OB, which is B. So that's why y is equal to b over A times x, because m is the gradient of this line, and that divided by that also we could say. Therefore we get from here y over b minus x over A equal to 1. Right? And so we have these two equations. This equation for the elliptical curve, and this equation for the straight line. This equation for the straight line. So I can write yc, that's the coordinate, vertical coordinate of point C, is equal to b squared 1 minus x squared over a squared. So yc is equal to b root 1 minus x squared a squared. And yq also I can get it from here. Okay, so yq, for the q, y is b times 1 plus x over a from there. Therefore cq is yc minus yq, because yc is this distance and yq is this distance. So those two subtracted from each other, I get cq over that distance y. And I have that one and that one, so I subtract them from each other, and I get this equation cq. And then if I differentiate this equation, partial of cq to partial of x, okay, if I do that, I get a relationship like that and that. Okay, that is partial of cq to partial of x is b times that parenthesis. So in here I have a and b, which are known. So if I put this equal to 0, I can get x, and I will do. Therefore, if we put here the differentiation of cq relative to x equal to 0, we obtain the maximum for cq, or y which is what we wanted. Because if we substitute for y in the previous expression for p over 4m, we get the minimum value for the collapse load. That in here, so x is equal to minus a over root 2. So I'm positioning this x in here. Okay, so that point C and point Q are known, and that is CQ. CQ is B times this. Obviously B is known because the ellipse is known, and that is B. And CQ is equal to B root 2 minus 1. Simplify that. So I put this into here. I get P over 4m 1 plus root 2 over B. So you can see that I'm using this plastic hinge. I can very easily find the load, the collapse load for a very difficult problem. You know, it's not an easy problem, this one example. This is difficult example. You cannot solve it in any other way unless you use this simulation, FEM simulation. You have to design your model and do all the necessary things you usually do in the finite element method, and it takes a long time just to do a simple problem like that. But in here I can get it very simply using the collapse load. Okay. Now in this case, in this example, we have again the ellipse, the oval link. Also we have the stud in here, but we have condition for this stud. We are saying that if the stud is insufficiently rigid. In the previous example, we considered the stud as not deformable, completely rigid stud. Okay, so but here it says if it is insufficiently rigid, it means that it can deform. It may yield in compression. Of course, we have ruled out any buckling, just the compression. So if it is under, if these loads are moving away, the link is compressing the stud, and the stud is compressed and deformed. Okay, and the deformation force is AY. A is the cross-sectional area of the stud, and Y is its yield strength. Now, this means that plastic hinges at the end do not form, because the force is spent to deform the stud and not to form hinges in here. Therefore, we would have hinges only in here. Okay, so that's one link, that's one link, that's 2, that's 3, that's 4, that's 5, that's 6. So here we have 6 link. Before we had 8 links. Okay, so we are going to solve the problem for this example, and these are the hinges, plastic hinges. Okay, and this is the diagram. Okay, so if we take for instance a perpendicular here and perpendicular there and connect these together, so we get this point C, D and E. That's the stud, and these move with the omega, small omega and big omega, because it's symmetrical about here. Also we have a force here, that's the reaction, AY, because we have a force along this stud, compressive in that direction, but that is the reaction. So if this moves with 1 meter per second, omega, big omega is 1 over IA. 1 over IA is the angular velocity of this AC, and small omega times CE, small omega times CE is equal to big omega times IC, and here we find the relationship between the big omega and small omega. Okay, IC over IA times CE, because big omega is 1 over IA, that's 1 meter per second. and therefore V, which is the velocity of point E, is equal to omega times CE. That's CE times omega gives the velocity at this point, and that would be equal to omega times CE is this omega times IC, so it's IC divided by IA. And therefore P over 2 again times 1. Now we have another force here, which is A. Y times VE divided by 2. That is for the link here. That's for the link here. And therefore 2m times omega. Okay, 2m times omega, because we have two big omegas here, and so that's what we get. And therefore simplifying this, we get P over 2 AY times VE, which is IC over IA divided by 2, and that's 2m, that's omega is 1 over IA. And here we get P over 4m is equal to 1 over IA minus that, which is AY over 4m times IC over IA. And now if we take this 4m divided by AY, because A is the cross-section of the stud, Y is the yield strength, and M is the plastic moment, fully plastic moment. So we know this, and so that's just a number. So IC becomes minus A minus X, that's IC, that's OA, okay, which is in the minus direction. If this is Y and this is X, then that is minus A, okay. Now we want point C in here, and that's minus X, so minus A minus X minus minus X is X minus A, and IA is equal to Y, okay, that's Y direction. So these are the coordinates X, Y of C. So P over 4m is Y 1 over Y minus 1 over C, X minus A over Y. And we could rearrange this in this way, okay, rearrange it. And that's again the equation of the ellipse. So you can get Y from here equal to this relationship, and dy by dx is equal to that from the ellipse. So here if we put d by dx P 4m equal to 0, differentiation of that with respect to x is equal to 0, that means that we get the minimum point, okay. So that's what we want, equal to 0, and you get this equal to 0, okay. So we use the ellipse relationship to get this, and therefore that is our equation, and we can get x from there. X is equal to a squared over a plus c, so x is obtained. So P over 4m, the minimum value for P over 4m is obtained by substituting this x in here, okay. So that is the minimum value that is going to cause the collapse of this